Space exploration is humanity's greatest adventure. It's about pushing the boundaries of knowledge and exploring the vast universe. At the heart of this endeavor are rockets, powerful machines that defy gravity to carry us beyond Earth. Understanding how rockets work is a journey into the fascinating world of physics and engineering. Rockets are marvels of technology, but their basic principles are surprisingly simple. They operate on a few fundamental laws of physics, primarily Newton's laws of motion. By harnessing these laws, we can propel ourselves and our instruments beyond the confines of our planet. Sir Isaac Newton's laws of motion are fundamental to understanding how rockets work. These laws, which were formulated in the late 17th century, have stood the test of time and remain as relevant today as they were when Newton first introduced them. They form the bedrock of classical mechanics and are essential for anyone delving into the field of physics or engineering. These laws, formulated centuries ago, explain the relationship between a body and the forces acting upon it, and the body's subsequent motion in response to those forces. Newton's insights were revolutionary, providing a clear and concise framework that could be applied to a wide range of physical phenomena, from the motion of celestial bodies to the mechanics of everyday objects, providing the foundation for rocket science. Without Newton's laws, the complex calculations required to design and launch rockets would be nearly impossible. Engineers and scientists rely on these principles to predict how rockets will behave under various conditions, ensuring that they can safely and efficiently reach their intended destinations. Newton's first law of motion. This law states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. This principle is often referred to as the law of inertia, highlighting the resistance of any physical object to a change in its state of motion. This is also known as the law of inertia. In the context of rocketry, this means that a rocket will not move from its position on the launch pad unless a significant force is applied to it. This force must overcome the rocket's weight and the frictional forces holding it in place. Imagine a rocket standing still on the launch pad. It is in a state of equilibrium with all forces acting on it balanced. The gravitational pull of the Earth keeps it grounded, and it will remain in this state until an external force disrupts this balance. It will remain at rest until a force greater than its weight pushes it upwards. This force is generated by the rocket's engines, which expel gas at high speed to create the necessary thrust. The engines must produce enough force to overcome both the gravitational pull and the inertia of the rocket. Newton's second law of motion. This law describes how a force acts on an object. It states that the force acting on an object is equal to the mass of that object times its acceleration, F equals sine ma. This equation is fundamental in calculating the required thrust for a rocket to achieve liftoff. It states that the force acting on an object is equal to the mass of that object times its acceleration, F equals sine ma. In simpler terms, the more massive an object is, the more force is needed to accelerate it. This principle is crucial when designing rockets, as it determines the amount of thrust needed to propel the rocket into space. In simpler terms, the more massive an object is, the more force is needed to accelerate it. For a rocket, this means that a more powerful engine is needed to lift a heavier payload. Engineers must carefully calculate the mass of the rocket and its payload to ensure that the engines can generate sufficient thrust. For a rocket, this means that a more powerful engine is needed to lift a heavier payload. The relationship between mass, force, and acceleration is a key consideration in the design and construction of rockets, influencing everything from the choice of materials to the configuration of the engines. Newton's third law of motion. Perhaps the most crucial law for understanding rocket propulsion is the third law, which states that for every action, there is an equal and opposite reaction. This principle is the driving force behind how rockets are able to lift off and travel through space. When a rocket expels hot gas out of its engine nozzle, the force of the gas moving downward creates an equal and opposite force that propels the rocket upwards. This reaction force is what allows the rocket to overcome Earth's gravity and ascend into the sky, ultimately reaching outer space. Understanding these three fundamental laws of motion is essential for anyone involved in the field of rocketry. They provide the theoretical framework that underpins all aspects of rocket design, testing, and operation. By mastering these principles, engineers and scientists can continue to push the boundaries of space exploration, sending rockets farther and faster than ever before. From the early days of rocketry to the cutting-edge technologies of today, Newton's laws have remained a constant guide. They are a testament to the enduring power of scientific discovery and the human drive to explore the unknown. As we look to the future, these principles will continue to inspire and inform the next generation of rocket scientists and engineers. One of the biggest challenges in space travel is overcoming Earth's powerful gravitational pull. Gravity is a fundamental force that attracts any two objects with mass towards each other. The more massive an object, the stronger its gravitational pull. Earth's gravity is what keeps us grounded and what makes objects fall to the ground. To escape Earth's gravitational pull, a rocket needs to achieve a certain speed known as escape velocity. Imagine throwing a ball upwards. The harder you throw it, the higher it goes before gravity pulls it back down. Escape velocity is the minimum speed an object needs to achieve to escape the gravitational pull of a planet or other celestial body. This concept is crucial for space exploration, as it determines the energy required to send spacecraft beyond Earth's atmosphere and into the vast expanse of space. For Earth, this speed is about 11.2 kilometers per second, which is roughly 25,000 miles per hour. This means that any object, whether it's a satellite, a space probe, or a manned spacecraft, must reach this speed to break free from Earth's gravitational influence. Achieving escape velocity is no easy feat. It involves meticulous planning, advanced engineering, and precise calculations. Engineers and scientists work tirelessly to design rockets that can withstand the immense forces and stresses involved in reaching such high speeds. It requires an immense amount of energy, which is why rockets are so large and powerful. The engines must generate enough thrust to overcome Earth's gravity, and this is achieved by burning vast amounts of fuel in a very short period. The faster a rocket travels, the weaker the gravitational pull it experiences. As it ascends, the force of gravity diminishes, allowing the rocket to accelerate further and reach the necessary escape velocity. Once a rocket reaches escape velocity, it can essentially coast away from Earth, even with its engines off. This is a critical milestone in any space mission, as it marks the transition from the intense energy expenditure of launch to the more efficient phase of space travel. To achieve the incredible speeds needed for space travel, rockets require vast amounts of fuel. This fuel is the lifeblood of any space mission, providing the necessary energy to break free from Earth's gravitational pull. Without it, the dream of exploring the cosmos would remain just that, a dream. The type of fuel used can vary, but most rockets use a combination of liquid hydrogen and liquid oxygen. These two elements are chosen for their ability to produce a powerful and efficient reaction when ignited. The process of handling and storing these fuels is complex and requires meticulous attention to detail. These propellants are chosen for their high energy density and efficiency. Liquid hydrogen and liquid oxygen are stored in massive tanks, often under cryogenic conditions, to keep them in their liquid state. Engineers and scientists work tirelessly to ensure that these fuels are kept at the optimal temperatures and pressures. Liquid hydrogen and liquid oxygen are stored at extremely low temperatures and are mixed and ignited in the rocket's combustion chamber. This ignition process is a marvel of modern engineering, requiring precise timing and control to ensure a successful launch. The combustion chamber is designed to withstand extreme temperatures and pressures. The combustion produces a tremendous amount of hot gas that is expelled through the nozzle, generating thrust. This thrust is what propels the rocket into space, overcoming the force of gravity. The design of the rocket nozzle is crucial, as it must efficiently direct the exhaust gases to maximize thrust. The efficiency of this process is crucial for maximizing a rocket's performance. Engineers continuously monitor and analyze data to ensure that every aspect of the fuel and combustion process is optimized. This relentless pursuit of efficiency is what enables rockets to travel further and faster, opening up new possibilities for space exploration. Stages of ascent climbing to the cosmos. Most rockets are designed with multiple stages to improve efficiency. Each stage is essentially a smaller rocket stacked on top of the previous one. As each stage expends its fuel, it is jettisoned, reducing the overall weight of the rocket. This staging system allows the rocket to shed unnecessary weight as it ascends, improving its fuel efficiency. The final stage carries the payload, which could be a satellite, a spacecraft, or even humans, into orbit or beyond. Beyond Earth's embrace, navigating the final frontier. Once a rocket escapes Earth's gravity, it enters the realm of space. Here, it encounters new challenges such as the vacuum of space, extreme temperatures, and the lack of atmosphere. To navigate this harsh environment, spacecraft are equipped with sophisticated guidance systems, thermal protection, and life support systems, if carrying humans. They rely on a combination of physics and engineering to maintain their course, communicate with Earth, and conduct scientific observations. The future of spaceflight, innovation, and exploration. The future of spaceflight is bright with promise. New technologies such as reusable rockets and advanced propulsion systems are being developed to make space travel more affordable and accessible. These advancements are opening up exciting possibilities for human exploration, scientific discovery, and even commercial ventures in space. From establishing a permanent presence on the moon to sending humans to Mars, the possibilities are truly limitless. Conclusion: our destiny among the stars. Rocket science is a testament to human ingenuity and our unquenchable thirst for exploration. By understanding the fundamental laws of physics and the challenges of space travel, we have unlocked the gateway to the cosmos. As we continue to push the boundaries of technology and our understanding of the universe, one thing is certain: our journey among the stars has only just begun.